Hey everybody, good to see you again. Mr. Smith here. We got a really cool one for you today. So far in Chapter 14, we have taken a look at conduction and convection as means of transferring energy from one place to another. And in talking about radiation, we get to a really interesting and broad, diverse one. So we already discussed how in the case of this building, you can see thermal energy being conducted. And so the recap, I think, is this building's probably built in the late 1800s. It probably has a wooden interior, so this is probably a big, heavy wood beam that you're seeing here. And what's going on is heat's being conducted from the inside of the building onto the outside brick. And what we skipped over was the fact that from the brick, it's radiating. So we know that because with an infrared camera, we are picking up infrared or thermal radiation coming from this part of the building and from the windows and from this really hot looking spot right there. The big thing that we want you to understand as you look at this deck is that even the cold parts of this building are also emitting thermal radiation because actually everything in the universe does. So here's a little recap. We're going to use the FLIR 1 camera attached to our iPads. And what it gives us a chance to do is to see somebody that's sitting here. You can see, for example, where they're wearing clothes. They're less bright, right? Well, it makes sense. The clothes would keep heat in and keep the thermal radiation from radiating out. But what the camera doesn't show you is that these parts over here, I should probably grab a white pencil there. These parts over here that look really cold, those are radiating thermal radiation too. And all the camera does is create with some software this image that shows the hottest things in the image as being warm and the other things as being cold or dark, okay? But in reality, everything in the universe radiates heat. So in the 1860s, James Clerk Maxwell published a thing called Maxwell's equations, and it was one of the most groundbreaking pieces of science in all the 1800s. And what he did was he linked together all parts of the electromagnetic spectrum with electricity and magnetism. So it's an incredibly great study that we'll be taking a look at. But there are a couple things here that I want you to get by way of reminder. For instance, we have what we call ionizing radiation up here. We have gamma, X-rays, ultraviolets. Those have the ability to knock off an electron from an atom, so they're ionizing. Visible light, it's red, orange, yellow, green, blue, violet. Infrared is what we know as heat, and infrared is this great big long band that spans like 3 orders of magnitude. So it's like a factor of 1,000 difference in the size of the wavelength or frequency for infrared light from the biggest to the smallest. So here's what was discovered. Before Maxwell, there was a time when scientists, and the guy's name was William Herschel, it's a famous astronomer, took white light produced by a candle, broke it up with a prism, and then put thermometers underneath the colors. And it wasn't understood what infrared was at the time, but what he figured out was that the thing that registered as the warmest was actually infrared. It was below red. And so we now know that infrared and visible light are different versions of the same thing. Well, they didn't back then before Maxwell, 1865. So what we're going to do is to dive kind of forward and backward in history. The big thing that Herschel took away was that temperature is related to the colors that we see. So if you take that simple idea and you jump forward to around the time of Maxwell, Gustav Kirchhoff is the guy that we talked about when we did Kirchhoff's laws for electricity. He had his hand in all sorts of different science, and what he showed was that black bodies, which are things that absorb all sorts of different frequencies of light, also emit all sorts of different frequencies of light, and the wavelengths that they emit depend in some way on their color. So again, what he did was to show that temperature and the color that a thing emits are related to each other. So we can sum it up with a really simple formula. It's very cool, and it's called Wien's Law. So you jump forward about 30 years from the American Civil War, and Wilhelm Wien discovers this relationship. It's based on experiment, not based on super deep physics or anything, but what it shows is that the color peak that's going to be emitted by a black body depends on its temperature according to this formula. So this is the first takeaway that you really need to nail down in this slide deck. It's really easy. So if we go and take 0.0029 meters times kelvins, and just divide that by the Kelvin temperature of the sun, 5,800 Kelvin, what it gives us is that the peak radiation is around, let's see, I have it here, it is 5 times 10 to the negative 7 meters, and that's equal to 500 nanometers. So why is the sun yellow? Well, that's why the sun is yellow. It's related to the temperature of the sun. So the surface of the sun is 5,800 Kelvin. 500 nanometers is right around the yellow in the spectrum. So the thing to know about this is that the peak of the spectrum is right here. And then as you walk on down, here's orange, getting into the red. You cross over into the infrared, and you should really notice there's this great big long tail of below red, infrared. So a thing that's warm enough to make yellow is also warm enough to make all these other colors or different versions of heat. So fair enough? There's a lot of heat made by the sun in addition to this little bit of visible color and this ultraviolet and other kinds of energy out here. Okay? So more on that later, but that's good enough for now. Next thing is if we progress, and it's actually historically kind of funny because you go backwards just a little bit. There was a formula that was discovered around the 1880s called the Stefan-Boltzmann Law, which is the second thing you want to write down. And we're going to look at our sun again, and what it gave you was the total power in joules per second or watts emitted by a thing. So what this does is it brings together all of the black body stuff. E is a thing called the emissivity of a material. And to make it easy, a black body has an emissivity of 1. It's a perfect absorber, and it's a perfect emitter when it's warm of light. So sigma is a thing called the Stefan-Boltzmann constant. It's one of the easiest constants in the world to remember. 5.67 times 10 to the minus 8. The units are crazy, but there they are. A is the area, and T is temperature to the fourth. So what we're going to do is turn our attention to the sun as though the sun were just a great big light bulb. How big? Well, we'll deal with it down here. So a couple facts about the sun. The emissivity of the sun is considered to be 1 because stars are generally thought of as being perfect black bodies. They absorb a wide range of different light energies that fall on them. So there you go. So emissivity is 1. It's a freebie. Area of the sun, what I'm going to use is the surface area of a sphere formula here, which is 4 pi r squared. And I go ahead and plug in the radius of the sun, which is 700 million meters. Do the math, and you get this big size right down here. So what I'd like you to do is actually stop the deck for a second, plug into your calculator, see what you get, and then you can compare with my answer right now. Ready? Okay. So here's my answer right now. Q over T for the sun is 3.95 times 10 to the 26 watts. So gigantic, gigantic power, enough to run a solar system on, right? So here's an amendment that I want to make right now. If you talk about environments where the temperature of the thing you're thinking about, so a person, and for example, the room, so we'll call the person T hot, and we'll call the room that they're exercising in T of the environment. If one of those things or both of those things is significantly more than 0 Kelvin, you have to use this version of the formula. So it's the same formula for Stefan-Boltzmann law, but what I've done is skip over the fact in the last slide that the environment the sun lives in is so cold, it's space. It's really 4 Kelvin. We could ignore it because the sun is so hot compared to that. But because this is T to the fourth, you'll find out, and as I work through this, that the room actually delivers significant energy to the person who's exercising in it, just as the person delivers energy to the room. So remember what I said in the first slide about the cold looking spots of the image delivering thermal energy. In fact, everything in the world delivers thermal energy when it radiates. So you'll see that right now. In this example, you might know this as an athlete. Human beings, 98.6 translates at the surface of their bodies to around 37 degrees C. A room that's 75 Fahrenheit, a pretty toasty environment for working out. So if you had that room temperature, 37 and 24 degrees C aren't that different. So let's go and play with those and see what happens. What I've done is I've adapted the E, the emissivity, for a human body. So if the question calls for human being emitting thermal radiation, you can use 0.7 for the emissivity. So I'm giving you the surface area of an adult man, so about 1.9 square meters of skin that you can expose to the environment. Sigma constant, temperatures raised to the fourth. So what I'd like you to do again, pause this, plug this into your calculator, check and see what you get. So what you should get right here is around 58 watts. And here's the thing. This temperature right here is pretty warm. For a man that's working out or a woman that's working out, we radiate baseline as human beings around 100 to 120 watts, even more when we're really working hard. So this is why 58 watts of thermal radiation net going to the environment means that you're going to really feel this heat build up on you in this room. Just for the fun of it, what I want you to do is go ahead and plug in a 40-degree Fahrenheit room and check and see what difference that makes. A 40-degree Fahrenheit room should give you an answer, if you plug it in over here, something like this, 132 watts radiated from your body to the environment. What a big difference that is. So because of the T4th, the temperature of the environment is a big, big deal. Okay, so that's it. Those are the important things for you to have as you get rolling in this topic. We'll see you in class. Bring questions and take care of yourself. Have a great day. Bye-bye.